Hello and welcome back to Automata Grammars and Computability. Today we are on Lecture 6, which is Regular Grammars and Context-Free Grammars. Before we move on to that, let's do a little bit of review. I want to remind you that regular expressions are more restrictive than set notation. We can write the Kleene star operator using set notation, and the pipe is just a set union, so there are some overlaps between set notation and regular expressions, but regular expressions have no memory. We can't count. Conversely, set notation is more expressive than DFAs. A language like A to the n, B to the n for n greater than 0 can be described using set notation, but not DFAs, because, like I said, DFAs can't count. All right, well, there's no way to draw a DFA or NFA for this, and we can't define this language with regular expressions. We knew that already because this is one of the languages that we showed was not regular by using the pumping lemma. But we didn't say what kind of a language it was. It's some kind of language, but it's just not regular. Now we have to look at a hierarchy of languages and see where it lives. And so this is the first time we're going to see that big picture of what we're trying to build to in terms of things that we want to be able to describe. That hierarchy of languages is called the Chomsky hierarchy. At the very bottom, which is where we've been so far, we have been talking about regular languages, and we have been recognizing regular languages using finite automaton. Going up a level, though, we have what are called context-free languages, which you can recognize using a machine called push-down automata. Moving up yet again, there's context-sensitive languages, and you can recognize those using linear bounded automaton. And finally, at the very top, you have recursively enumerable languages, which you can recognize using Turing machines. This gives a big picture in terms of the kind of expressiveness that we can have with languages. So we have started to see context-free languages and above because we've been talking about languages for which the pumping lemma does not hold. And this is where we're going to actually go a little bit more in depth into those context-free languages. All right, I've mentioned languages and machines already. The new thing that we're going to have here is going to be something called grammars. With regular languages, we've been using regular expressions, DFAs and NFAs, and of course in programming you can use regex to find strings. And there is a concept of something called a regular grammar, but we skipped that. However, now that we're moving up in the hierarchy, we're going to start talking about something called grammars, which will help us better understand context-free languages. For now, just a grammar consists of a collection of substitution rules, which are also called production rules, and variables. Now, rather than using a language, which is a set of strings, we can talk about the hierarchy in terms of grammars that are accepted. At the very bottom, we have regular grammar, and then moving up, we have context-free grammars, context-sensitive grammars. So far, the names have been the same as for the languages. And then at the very top, we have what's called unrestricted grammars, which go along with recursively enumerable languages and Turing machines. What we're going to do right now is talk about context-free grammars and context-free languages to get an understanding of how those production rules and variables work, at which point it should be easier to understand regular grammars. Okay, so a context-free language consists of, as mentioned before, a substitution or production rule and symbols. The symbols consist of variables, which are usually denoted using capital letters, which includes something called a start variable. and it includes another type of variable called terminals. Let's look at an example. I'm going to write here the letter A, and I'm going to write an arrow to 0, A, 1. And then I'm going to do A to B, and then I'm going to do B to hashtag. These are these substitution rules. Basically, I'm saying I can replace the letter A with the string 0A1. I can replace the letter or variable A with the variable B, and I can replace the variable B with the symbol hashtag. So the variables here are A and B, and the terminals are 0, 1, and hashtag. Now, rather than talking about a language as a set of strings alone, we are now talking about production rules that are going to generate those strings or elements of the language. It works as follows. You're going to start with writing the start variable. Generally, that's the left-hand side of the topmost written rule. Find a variable that is written and a rule that starts with that variable. Then replace that variable with the right-hand side. Just keep repeating step 2 until no variables are left. Let's look at our prior example with A going to 0A1, A going to B, B going to hashtag, and we had the variables A and B and the terminals 0, 1, and hashtag. In this case, A is my start variable because it's the one written in the topmost rule. Following this along, you start with A, and you can pick a rule. So I'll pick 0A1 to replace it, and then I'll continue. So I'll say 0, 0A1, 1, and again 0, 0, 0A1, 1, 1, and then I'll replace it with a B, 0, 0, 0, B, 1, 1, 1, and then I'll replace that B with the hashtag. One way to say this is you can say that the grammar generates this particular string. You can also follow along with a parse tree. Which would have you say A can go to 0A1, and that A can go to 0A1, and that A can then go to 0A1, then B, then hashtag. And so I end up with the same string that I would have, that I got in the previous, just previously. Now that we've worked through the example of a particular context-free grammar and shown the production rules, let's actually formalize the definition. A context-free grammar is a four-tuple, V, sigma, R, and S, where V is a finite set of variables, which are known as the non-terminals. Sigma is a finite set. It's disjoint from V, and it's the terminals. R is the set of rules, and it's a subset of V cross sigma union V star. So what this means is with V, that's one of the non-terminals, and it's going to go to this rule, which is going to be some set of terminals and non-terminals repeated in some manner. Normally, of course, instead of writing alpha, comma B, we write production as alpha right arrow B. So that's normally how we would write a production rule. And then finally, S is the start symbol, and it's one of the symbols in V. Let's look at that example again and rewrite it in terms of the formal definition. So the finite set of variables that I had for my grammar, we'll call it G1, is V is equal to AB. And I have sigma, which is equal to 0, 1, hashtag. And my start symbol is the symbol A. And then my rules are the 3 rules that I had, which is A goes to 0, A1, A goes to B, and B goes to hashtag. So if I write V, sigma, S, and R, I'm describing this whole thing as a grammar. It also turns out I can describe it as a language by thinking about all the strings that I could generate. And if you follow along, you'll notice that since A is always replaced by 0, A1, and then B is replaced by a hashtag, that my language for this grammar G1 is going to be a bunch of copies of 0, a hashtag, and then a bunch of copies of 1 with the same number of 1s as 0 for n greater than or equal to 0. Another way to formalize this definition is with something called the language of the grammar. So I'll show that definition in the next page. The language of the grammar is a set of strings that can be produced by that grammar. If U, V, and W are strings of variables and terminals, and A can be substituted with W as one of the rules of the grammar, then UAV yields UWV. And this is normally written with a double arrow, so UAV double arrow UWV. Now, we're going to add a little bit more of notation to this. We're going to say U double right arrow star W if either U equals V or there's a sequence that exists U1 through UK for k greater than 0, where U can yield U1, can yield U2, all the way up to W. So it doesn't really matter how many steps it takes as long as you can get to that final string. And now that we have this notation, we can say that the set W in sigma star such that S yields with star W is the language of the grammar. Let's break this down a little bit more and let's go back to that example. Remember that we had this example of production rules where A can be replaced with 0, A1, A can be replaced with B, and B can be replaced with hashtag. And my symbols that I had was A as the start variable and B, and my terminals were 0, 1, and hashtag. And I also drew earlier a parse tree showing that if you started at A, you could go to 0, A1, and so on and so forth. And if you follow along, you can start to see that because this A can always be replaced with a 0 on the right and a 0 on the left and a 1 on the right, that you are going to end up, no matter what, with 0, then a hashtag, and then a 1 the same number of times. So it's the language that's going to get generated is 0 to the n hashtag 1 to the n for n greater than or equal to 0. And just a small reminder, we looked at this language a to the n, b to the n, for n greater than 0. And although I changed up the symbols a little bit, these two are pretty similar. And you know also that this language is not regular. On the previous slide, I started to hint to you that 0 to the n, hashtag 1 to the n was similar to the language that we had previously of a to the n, b to the n. And this is a language which is context-free, and it's not regular. We know that because of our previous proof with the pumping lemma. Something that I want to do here is give you a chance to try and think of some production rules for this language. I have this language, a to the n, b to the n, and now let's say that G is the context-free grammar, V sigma, P, and S, where the start symbol is just going to be the letter S. My sigma is the letters A and B, and P is the production rules. So take a moment and try to write down the production rules that go with A to the N, B to the N. They should look similar, but a little bit different than before. You should have come up with something similar to having S going to ASB. So before we had A going to 0, A, capital A, 1, but now I just have A S that goes to A, capital S, B. And maybe the trickier part in this question, that was a new thing you had to think of, was the fact that I can't have that hashtag, and I don't even have that letter in my alphabet. But one thing I can have is an epsilon. So I can have a production rule that allows me to have epsilons, at least in this version. So now that I have a description of the context-free grammar that goes along with the language A to the N, B to the N, you can conclude that L is equal to L of G, so that L is a context-free language. Of course, you really need to prove this to be sure that L is a context-free language. I'm not going to show the proof, but in order to show that the L that we described above is really the language that goes along with the grammar whose production rules we came up with, we have to show both that L is contained in L of G and that L of G is contained in L. If you're curious, this is worth looking up, but the proof is skipped in this video. Let's finalize this video just by talking about regular grammars. We learned that a context-free grammar is a type of formal grammar, and the production rules are of the form A right arrow beta, where A is a non-terminal symbol and beta is a string of terminals and or non-terminals. A regular grammar is also a formal grammar, and it has production rules that consists of non-terminal symbols and strings of terminals and non-terminals, and it can have epsilon. The requirement for regular grammars, though, is that they're either what's called left or right. So the way that we write the production rules is more restrictive than the way that we did it for context-free grammars. Let's say A and B are the variables and non-terminal variables, and alpha is a terminal. Then you can have a right regular grammar where the rules have the form A goes to epsilon, A goes to alpha, or A goes to alpha B. And with the left regular grammar, you have rules of the forms A goes to epsilon, A goes to alpha, as we saw before, and A goes to B alpha. So you can see that I can only append the terminal symbols to the either left hand or right hand side of the other non-terminal value. So it looks a little bit different than what we required from context-free grammars. let's look at an example of a regular grammar. Let's say I have the start symbol S, and it can go to AS or BA. So something new here, just a little bit of notation. Instead of writing two rules, I write one using a pipe before an or. My other rule is A goes to CA or epsilon. Now the best way to start to figure out what the descriptor for a language is just to start drawing some examples of what the strings could be, and starting to get a sense of the patterns. And so you would just do this for a little bit and just sort of get your hands dirty, is how I like to say it. And then if you do that enough, you should be able to hopefully come up with what kinds of patterns this can take on. So what I wrote here is not exhaustive by any means, but it gives you a sense of what to try out if you were trying to figure out what this language represented. If you do this long enough, you can see that the grammar produces the language produced by the regular expression A star B C star. Okay, so this is where this particular video ends. We have talked about context-free grammars, production rules, and regular grammars. That's all I have for now. Thanks for watching.